Hello and welcome to Session 3 of the Unmanned Systems Virtual Conference, applying a MOSA strategy for unmanned systems. My name is John McHale, Executive Vice President and Group Editorial Director with Military Embedded Systems Magazine and the SOSA Special Edition, and also host for today's event. To learn more about military embedded systems, please visit militaryembedded.com and check out our articles, blogs, and podcasts on military technology. All right, our session speakers, are Roger Hosking, Director of Sales of Mercury Systems, Saddle River, New Jersey, and Mark Littlefield, Director, Embedded Computing Solutions, Elma Electronic. Session 1 is sponsored by Mercury Systems and Elma Electronic. The Unmanned Systems Virtual Conference platform sponsor is Wind River, and the event is hosted by Military Embedded Systems Online and Open Systems Media. Before we begin, I have some housekeeping items. This and all Open Systems Media virtual events are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. This session will consume about 40 to 45 minutes, leaving the remaining time for the question and answer session. You'll find on your console window an area where you can enter your questions in real time. If you have a question pertaining to the event operation itself, one of our technicians will get back to you during the session. We encourage you to ask questions throughout the session while the question is still fresh in your mind. We'll address as many questions as we can during the closing Q&A portion. If you have a question for a specific speaker, please note so at the beginning of your question, or I will offer the question to all of our speakers. Please note that as much as we'd like to, we may not get to all your questions today. In that case, someone may get back to you after the event with more information. On the console, there's also a handout section, and that's where you can find the slides being presented today. This session and the overall event will be archived online at the URL shown on your screen and be available within 48 hours. Once up, it'll be available for 1 year. Now I'm pleased to get this session started with Mr. Roger Hosking. Roger, take it away. Roger is coming. We 1 second. We have a slight open for difficulty. Give Roger a 1 second. Our technical staff is working on getting him back. And here he comes. And I promise you, it's well worth the wait.
Can you hear me?
We can hear you, and I told the audience it's well worth the wait, so bring it on. Let's do this.
All right, let me just go back here to the screen. Thank you for your patience, and thank you all for joining us today. So today what we're going to do is look at a little bit about unmanned systems and how the modular open system architecture approach has affected them. So I'm going to advance the slide, and let's see, where is the arrow for doing such? Here we are. No. I'm back on, let's see. The presentation was there, but there was no slide advance. Okay, there we go. So let's try it again. Everybody, thanks for your patience. These are the topics we're going to be covering today. We basically start out talking a little bit about MOSA and then a little bit about how SOSA evolved from that. Go over some of the types of systems for unmanned applications, what they need, and then what MOSA and SOSA then brings to the table to help these systems become realized and supported for what they need to do. And then we'll take a look at some solutions that will help these unmanned systems, and then some takeaway information for more information about the standards. So what really started MOSA was a 2013 directive by the DoD that was to enhance competition, to facilitate technology refresh, to inspire innovation, to save cost, and then to improve interoperability among and between the vendors. So this is really the essence of what open systems are all about, and it was called MOSA. As a result of that, each of the three services decided their own approach of how to achieve the objectives of MOSA. And the Navy, for example, developed HOST, the Hardware Open System Technology Standard. The Army developed CMOSS, and the Air Force developed OMS for Open Mission Systems. Now, what these initiatives within each of the three services did was it pulled into things the standards that they thought would be good to implement their needs. And there are a lot of these standards that were pulled in came from common standards like OpenVPX and other software standards, but they had a lot in common. And those three arms led into the need for a more common consolidated standard called SOSA. And that's the SOSA initiative was born by recognizing that there was a lot of commonality among what the three services needed. And so each of those three have now merged into the SOSA consortium, and it's formed under the Open Group, which is a standards organization. A lot of members of SOSA also contribute to the VITA organization, where a lot of the standards you'll find in SOSA come from. A big milestone happened in September of last year when the SOSA consortium released their technical standard 1.0. After years of work, 3 years or more of work, it was published, and it was done by over 100 different sponsors, members, principals, and so forth. So it was a big joint effort among the military, DoD, the vendor community, and the academia. So it was really a big joint effort. The reference architecture, which is described in this standard, covers hardware, software, and electromechanical. The most complete part of the standard right now is the hardware and the electromechanical parts. The software effort is still underway. The good news about this is that this specification is open for worldwide use, and so you'll see other military organizations outside the U.S. become very interested, wanting to do the same thing that's being done in the U.S. And so they will be using this standard and are very interested in finding products available that will be SOSA compliant, conformance. So this now will lead also to procurements coming from DoD that will specify open standards and specifically reference SOSA. We've already started to see these requests for information, requests for bids come from the government. Unmanned vehicles really cover a huge different class of platforms, from very large platforms to very small platforms. And here's an example of the 4 general classes of unmanned vehicles: the unmanned aircraft vehicle, unmanned ground vehicles, surface vehicles, underwater, and on the surface. So it's really underwater unmanned vehicles as well. So this is a picture of kind of what they look like. There's a lot of different sizes, a huge variety. Oops, did I just lose my camera? Let's see. Somehow it seems that I went to, maybe you could help me, Ryan. I must have clicked the wrong
way,
button.
Roger. They'll be back in a second. John.
Okay. Here. I must have done something. Okay, let me click through rather quickly and get back to where we were. Okay, I think we're back now. So let's take a look at some of the critical needs for unmanned vehicles. Of course, the obvious one is reduced size, weight, and power. And this, of course, is true of especially of the smaller vehicles, but also true of any airborne vehicle. They also have to be really robust to operate in a lot of different hazardous areas where even troops might not be able to go because of the severe danger of the area. And then, because of what they're doing, is they need to be connected to a huge array of different types of inputs and outputs, cameras and antennas and sensors and transducers and all kinds of sensor information, and hence the name for SOSA, Sensor Open System Architecture. It's all about connecting sensors to processing elements to make decisions. And the other major part of a lot of these unmanned vehicles is the need to do autonomous computing and decision making. And this requires increasingly more and more artificial intelligence and machine learning capabilities to become aware of the environment, to look at what's coming through the sensor, and make a decision on what to do about what's perceived, make real-time decisions, often autonomously without the benefit of a human in the loop of trying to make that decision. So these are increasingly more powerful and more capable of making quick, accurate decisions that are needed in these types of vehicles. Other types of requirements include the sensors have to be more sensitive and be able to require a higher dynamic range for signals, for example, radio signals and cameras and so forth. They need better resolution, better dynamic range. And also the signals that are out there are increasing in complexity. Some of them are encrypted and they have to be decrypted. There's a lot of different complexity. And then bandwidths are increasing because of information that's being carried to and from these vehicles to a central facility, and operational frequencies as high as 300 gigahertz for a lot of the new radars. Another common thread is that a lot of these vehicles will be using electronically steered antennas, or AESA, and for things like synthetic aperture radar, very popular and very common. What this allows you to do is to steer the directionality of the antenna for both receive and transmit, to aim energy and to receive energy in very specific directions. This really allows you to track targets very, very quickly, multiple targets, without having to mechanically steer a large antenna structure. So very, very popular. They're getting more powerful every day. Now, what SOSA does is it draws really heavily from a lot of open BPS specifications, but only certain parts of those specifications. And this is a list on the left of what kinds of specifications are drawn by SOSA to define primarily the hardware architecture for the reference architecture described in the standard. Here's a list of some of these standards that call out certain board characteristics: mechanical, thermal, power, cooling, and then also system management. These are all parts of these specifications are pulled into the SOSA standard. One of the standards that VITA evolved was the VITA 49, which is Radio Transport Protocol, which is also used in the SOSA. What it does simply is it tries to get rid of a lot of the what's called stovepipe architecture, which involved a lot of wiring. All these red lines here represent RF cabling that has to go for the RF signals down through distribution and so forth. This is a big problem in terms of complexity and maintenance and for flexibility. And then there were dedicated links from the digitizers. These would be the A to D converters to the different signal processors. This concept has been replaced with the VRT concept. What VRT does is it assumes that you digitize the signals, the RF signals, very close to the antenna. And then from there on, the digital signals are transferred across a digital network to the destination, and all of the routing and the connectivity is done over a switched digital network. So you can see in this case that the number of RF connections and the length of those connections is much shorter, and the flexibility of the switched network gives you the ability to have different applications, the same data going to multiple destinations and so forth. A very, very flexible arrangement. The other thing SOSA does is it says all of your I/O signals for the plug-in cards in the SOSA backplane have to go through the SOSA backplane. This includes RF and optical I/O, as well as the electrical signals as well. So what we're seeing is some new standards that came through VITA that cover backplane I/O for a high number, in this case 20 RF connections across the backplane. And here there's two MT optical ferrules with 24 optical lanes each. So these are enablers of the goals of what SOSA is looking for. That is to get rid of the front panel cables and use as much as possible backplane to simplify maintenance and improve reliability for SOSA. I just made a list of things that I thought were very significant in terms of impacts on unmanned vehicle designs. And some misperceptions are that SOSA specifies a system. It does really not. It specifies only the components within the system. That is typically the plug-in cards and the chassis and so forth. And only a few of the open VPX profiles for plug-in cards are used within SOSA. Ethernet is very strong. It's replaced a lot of the PCI Express and other interfaces in embedded system design. And it really covers connections between the cards within a card cage and between systems. And those Ethernet signals can use Ethernet for both control and payload data, and that improves interoperability. That is to use a standard format, a standard protocol to move payload and control data. We mentioned the backplane I/O. And SOSA really doesn't control some of the external sensor-specific subsystems. We'll look at those in just a minute, but it does want those external signals to be compliant with the SOSA interfaces, like the multi-gigabit Ethernet inputs and outputs that are called out in SOSA. Some new technology is for AI and for machine learning is given to us from the Xilinx ACAP Versal AI Core FPGA. It's really a heterogeneous processing engine. If you can see kind of across the top diagram from left to right, you see a farm of ARM processors. You see programmable FPGA logic in the center. And then you see AI engines and DSP engines as well. All of these different processing resources are all on a single chip, and they're all connected together with a network on chip that joins them to each other and to the resources down below, which gives you memory and interfaces like multi-gigabit Ethernet I/O to the outside world. So this kind of very nice computational power is very, very powerful. As we saw, it's needed for autonomous platforms. We also then have an application where one of those examples is a 6U VPX card that uses two of these ACAP Versal Core devices. It gives you these machine learning, artificial intelligence, and it really allows you to adapt to new applications and change the configuration by shifting the task from one of the processors to another one, depending on what the task is. So it's very much in line with the principles of SOSA. Another very powerful chip is the RFSoC. I think many of you have probably heard of it. It's got A to D converters, D to A converters, very high-speed multi-gigabit serial interfaces, and it's really a complete system for a phased array antenna, for example, to receive and do all the necessary signal processing at the front end level for radar and comms systems. Now, if we take that chip and we put it inside of a box, you have something that could look like this. And this is really a complete remote 8-channel RF-IF transceiver that could be used to connect up to a phased array antenna for using one of these remote acquisition subsystems that I talked about a little bit earlier. So the nice thing about this is that you can use it, let's say on a remote tank, for a terminal that would allow you to acquire signals, have it mounted up on the mast of this tank with a phased array antenna. The antenna signals are connected to the some RF circuitry and power amplifier, and then over to the RFSoC box to form a beam-formed antenna array solution. It is then connected up to a 3U Open VPX SOSA card cage over dual 100 gigabit Ethernet for data and 1 gigabit Ethernet for control and status. Really it lined up with how SOSA wants to connect to the outside world. So what does really SOSA mean for vendors and customers? It really gives you all the principles that we talked about in the first slide, the objectives of MOSA, the innovation, improved life cycles, and it gives another way for primes to get into market more quickly, into production more quickly, because a lot of these solutions then can come from lower tier vendors that are more agile in developing SOSA solutions that the prime can then use to speed up and lower risk for him to deliver. The challenge is to provide enough SOSA products to satisfy all the requirements of systems. And right now, the technical standard has been released. There's going to be more product out there, and there's going to be more certified products out there as well. So really, SOSA has now over 100 member organizations. We've released the standard. It has lots of different products available as SOSA aligned products. These are now ready to go into the certification process. We've got a lot of benefits for every side of the industry, that is from the customer to the suppliers. It really benefits all of them. And even though there may be some challenges at first to get into some of these new principles, long-term advantages are really clear to all the stakeholders in SOSA. So here are some more useful information you can gain by clicking on these links. You have some from Mercury and some from on the Pentech website, a lot of articles. And then the SOSA technical standards is available here. Again, it's available for download and worldwide use. If you'd like to get involved in SOSA, I invite you to do so. Here's the link for membership FAQ. So with that, thank you very much for attending today. I hope this was useful. And now I'm going to turn over the presentation to Mark Littlefield of Alma Electronic. Take it away, Mark.
Great. Thank you, Rob. And I'll be talking about the kind of the same topics that Roger was talking about. A little different take on things, but you'll see. So as Roger mentioned, unmanned systems can sometimes have really severe swap constraints. Sometimes not so much, like the Global Hawk on the right. Maybe it's not so much swap constrained as some of the other platforms that you see here. So this is a typical problem that system integrators are always facing. In addition, and as Roger kind of pointed out, there's some pretty heavy processing and bandwidth requirements that are coming down the pipe, whether it's the sensor payload that requires the data and the processing, or the actual vehicle itself, processing for navigation and control. So MOSA, while Roger pointed out that it's kind of the hot topic, there's been some real strong initiatives. As a basic idea, isn't exactly new. It's been around for a while, using standards-based off-the-shelf products to build up your systems. I mean, VME has been around for many, many years. There's Compact PCI, ATCA, Micro TCA, but VPX is the real workhorse today. The one problem was that while they were captured by standards, the standards allowed for customization by the individual vendors, and they often suffered from incompatibilities and vendor lock. And so the newest MOSA initiatives that like SOSA are really intended to kind of drive that out of the standards environment and make it so that pieces plug in together and are expected to just work. So the problem is that, while VPX is really, really powerful, it's used in a lot of different environments, There are just some systems that are too small for VPX. The swap constraints are just too tight to be able to successfully use VPX. Few examples are common launch tube based applications. Common launch tube is 5.5 inches in diameter. It's too small for 3U VPX. And there's the UAVs and other types of sensors and what have you that need to launch out of common launch tube. CubeSat, another very small platform that is too small for 3U VPX. There's unmanned air or underwater vehicles, things like that can be quite tiny and simply can't fit VPX. So what's been done in the past, traditionally custom systems were employed. People design their own hardware. But that's expensive, it's not very portable, just not very MOSA-like. SOSA as an organization identified this early on and formed the small form factor subcommittee within SOSA to try to find or develop a solution to this, to come up with a modular open systems architecture that was significantly smaller than 3U VPX to address these problems. But the trick was, though, that we needed to maintain alignment with the SOSA principles of modularity, scalability, interoperability, interchangeability, multi-mission, and so on. So there's kind of two paths that one can go down using COTS hardware. Now I'm using the term COTS. It's maybe not exactly MOSA, but it is things that are off the shelf, relatively affordable, standards-based, and so on. So I'm going to talk a little bit about that, and then I'm going to talk about the new VITA 90 or VNX Plus that's being worked within VITA and within SOSA. But I'll start a little bit with the small integrated mission computing platforms. Those are typically characterized as physically compact, fully integrated computing or networking platforms. These are things that are self-contained. They just really need power. They are pre-qualified for environmental testing. They are usually pretty easy to customize, and numerous suppliers have them. I mean, Elma has a line of computing and networking products that are like this. Mercury does. There's other suppliers that do as well. So some of the features of these integrated mission computers are they're typically fanless, not 100%, but typically they're fanless, so they're convection cooled. They're IP67 usually, which means that they're immune to immersion, sand, dust, other contaminants, things like that. They're typically single processor, somewhere in the range of 15 to 45 watts of TDP. With a sweet spot around 25 to 35 watts. You get much higher than that and you start running into thermal issues with no fans. Smaller than that, and they're maybe not quite so interesting as far as sensor processing goes, at least for payloads. They're usually built using industry-grade standards-based hardware like ComExpress or SMARC and things like that. There's some others that are used, and like I said, configurable using things like Mini PCI Express, M.2, or XMC modules. So as far as rugged testing goes, there's a wide set of tests that can be available from MIL standards or DO testing, like DO 160. But this is kind of a baseline. This is Elma's baseline that we use for all of our systems. Many of our systems do other testing, like perhaps explosive atmosphere or rapid decompression that might not be on the baseline list. But this is a pretty common set of tests that are used on systems like this. So typically temperature testing, shock and vibration, humidity, water immersion, blowing sand and dust, altitude, both operating and storage. We do power input and transient protection testing against MIL standard 704. We typically also do the RF susceptibility and radiated conducted emissions testing against MIL standard 1275 and MIL standard 461. Those are particularly important and often some of the most difficult tests to pass. The reason for doing all of these tests ahead of time, before we maybe even sell the first unit, is that we want our customers to buy those units knowing that they've passed these tests and that they can rely on them then when they're integrated into their system to pass their final qualification testings that their whole system needs to undergo. It basically gives confidence to the platform. So there's advantages and disadvantages. The advantage is that it is COTS based, usually Intel or ARM, but there are others. Like we offer an NVIDIA based TX2i based platform. There's standards based expansion, so it's pretty easy to expand, and there are industry standard IOs like Ethernet, USB, RS-232, video, things like that. It's off the shelf and pre-qualified, as I mentioned, raises confidence. It's much quicker time to deployment than building your own from scratch. And using modern multi-core processors means that it can usually do more than one thing at a time. You can often do multiple tasks with a single unit, and it's usually a fairly affordable way to build a system for these small platforms. Disadvantages are that it's difficult to scale. If multiple processors are needed, you basically need multiple units. And then I say no standard footprints. There's actually a VITA standard for footprint, but it's not a very commonly followed one. It's just never been really well adopted. And so in a sense, yeah, it's off the shelf, but it's not really very MOSA, if you will. So switching gears to VITA 90, VNX. VITA 90 was derived from VITA 74, which some folks might recognize as VNX. It's significantly smaller than 3U VPX. It's about 70% smaller, about 1/3 the size than a 3U VPX on a per slot basis. And it's a pretty good fit for SOSA attributes as far as scalability, modularity, and so on. It supports both backplane and cabled connections, which is kind of nice. But while we picked it for SOSA, we realized that it needed some significant enhancements before it was really, really useful for SOSA. And that's why it's now been spun out into VITA 90 or VNX Plus, its own standard, because of the enhancements were a big enough jump from the original VITA 74 to make it worth changing. So in VITA and in SOSA, there's activities underway to address these shortcomings from the original VNX standards. Some of the things that were identified early on were a lack of slot profiles. In SOSA, we're very particular about wanting slot profiles that are fully defined so that you can take a card out of a backplane, put a different card in the backplane, and with the expectation that it'll just work. Excuse me. So we needed payload profiles, we needed switch profiles, we needed radio clock PNT profiles, and so on. There were also no apertures defined in VITA 74 for coax and optical blind mate connections, like what Roger mentioned for VPX. Those connections were needed, so we needed to define that. There was no defined support for VITA 46.11 out-of-band system management, which is a very important piece of SOSA. Out-of-band system management is very critical and central to the SOSA technical standard. There was no defined power modules, which was seen as something that was needed. And there was folks that wanted to see alternate mounting mechanicals. Excuse me, specifically wedge locks, or the ability to directly surface mount a module onto, say, a bulkhead or a sidewall or something like that. So first thing we did is in working with Samtec is that they had different versions of the original C-Ray connector that was used in VNX. And so we decided on two additional connectors. In addition to the 400-pin connector, there's a 320-pin connector with a half aperture, and then a 240-pin connector with a full aperture. So that aperture gives space to allow us to put in optical and RF coax connectors. We then actually defined those optical and coax connectors. Specifically, there were three that were chosen. The full aperture hybrid, which has two MT connectors, MT by 24 connectors. And then with regards to coax, there's two different types of coax that are defined here, 16 20, size 20 and 4 size 16 contacts. Then with the half aperture, we did two different ones. One includes two MT connectors, again, the dual 24 fiber connections. We see that mainly as being kind of interesting for switches, but certainly could be interesting for payloads as well. And then the half aperture hybrid, which has one MT connector along with 6 coax contacts. Next, we turned attention to slot profiles. We spent a lot of time and effort to really optimize this. Starting first off with the S0 utility segment, we really kind of tightened that up from the original VITA 74, redefined it, updated it, and made it so that it's truly, a tight and universal utility segment. Next, we defined an S1 communications segment, a common communications segment, mainly targeting payload profiles. So we used the same model as VPX did, including the data plane, or in data planes rather, expansion planes and control planes. I should mention that in these pictures, it's impossible to read the content, but the green sections are the utility segment, the orange and the yellow are the and the red are actually blue, orange, and yellow are the communication segments. And then we defined this thing called an overlay segment, or S2. And that contains both copper, which is shown in purple in these, and the aperture region, which is sort of in the gray area. And that allows for really the specialized profile definitions that will be captured in VITA 90.1. Now, we knew immediately that we needed switches and radio clocks, and so we tackled those actually as our first real profiles that were fully defined. And so with the switch profiles, we got 2 switches, one with no aperture, with 7 data planes and 8 control planes, and another one with a half aperture for optical, with 5 data planes and 5 control planes. Then we turned attention to radial clocks. We started with that template for the payload with the overlay region, and we created a 320, using the 320 pin template, created a radial clock with 7 ref clocks and 7 aux clocks, along with all of the signals that would be available to an SBC, so data plane, control plane, expansion plane, and so on. Some folks thought that, well, most systems are probably going to be could be satisfied with that. There are some cases where we needed much larger, and so we put away the template, and we created a full radial clock profile, if you will, with 25 pairs of ref clocks and aux clocks. So for even some of the largest systems you can imagine for using this hardware, that profile could be used. Just going to mention briefly that we are looking at using wedge locks and direct mounting hardware. This is in work. This is just an early proposal. Hasn't been validated or finalized yet, but it's still in work within VITA. So there's work outstanding. I mentioned here's short VPX, or SVPX. As short VPX is another option, if you will, for small systems. It's about 65% of the size of 3U VPX. So it is smaller than 3U VPX, but not as small as VNX Plus. But both are options for building very powerful modular systems with using MOSA and SOSA profiles. We have some work to do, though. We need to complete the base standards, which are under work today. Short VPX is complete and in VITA today. You can look it up on VITA 48.2 if I remember correctly. We are targeting to have complete SOSA technical content in the version 2 snapshot 2, which is scheduled for the second half of 2022. And there is work underway actually on products based on this. Even though the standards are still in work, folks are blasting ahead, and you'll see those first products available before the end of this year. So there, again, like everything, there's advantages and disadvantages. Advantages, this is modular, so it's got a distinct advantage over the previous approach I mentioned. Permits multi-processor and scalable systems. It's captured within the technical standard, although if you look today, you'll find mainly placeholder elements. Snapshot 1 will have more content, and then, like I said, snapshot 2 is expected to flesh that out. And then disadvantages. It is very much smaller than 3UVPX, and so one thing is you're going to be limited in power to about 25 watts per module. Although there are ways to go beyond this, the physically smaller, you're going to be. It's tricky to get the heat out of these modules. It's a new standard. The standard's still in work, and as of today on VITA 90, there's no product out yet. But like I mentioned, product is expected before the end of the year. So in summary, you do have options for building systems for these small unmanned vehicles, whether they're ground-based, sea-based, or aircraft, or even space. You can use MOSA-based components and MOSA-based approaches to build these systems. Okay, and with that, I will pass it over to John.
Disappearing act for me, but I came right back. So excellent presentation, gentlemen. I really appreciate it. And now we're going to get right to the audience questions. And my first one is for Roger. What is the SOSA certification process? And do you really call it certification, Roger? I thought it was conformance and alignment.
Well, it's really two pieces. One part is that you have to have third-party conformance testing to make sure that the specifications in the standard, the reference architecture standard 1.0, are met, and so you need a testing or a validation authority for conformance. Once that authority says yes, this product is conformant, a report goes back to SOSA, which then certifies that product as being SOSA certified product. So it's really in two stages.
Okay.
So, John, if I could add to that, though,
Yeah,
I'll add that the process for certifying SOSA product is still in work. It is a pretty daunting task, as you can imagine. The documentation that's involved and the test structures that are needed to be able to exercise hardware and software components to make sure that they're conformant with the standard is challenging. But so we're working hard on it.
I also think that a lot of companies are trying to build a business case for becoming, say, a validation authority. It's an interesting challenge. Can we make money doing this without charging too much and making it onerous to moving the standard forward? So it's an interesting business case, I think, that a lot of companies are trying to struggle with. The test companies like Tektronix and others. Is this a valid business model for us to go forward? And anyway, work is in progress, as Mark said.
Okay, got a question here for Mark. You did talk about short VPX a little bit toward the end of your presentation. Could you expand on that and where it comes from and how it fits into the VITA ecosystem?
Sure. When we first kicked off small form factor subcommittee in SOSA, that was brought up as an option. Basically, what it is, it's the same as 3UVPX, but rather than being 160 millimeters deep, it's only 100 millimeters deep. Otherwise, it's identical to 3UVPX. So that was pretty, easy, low-hanging fruit to grab. And so we worked on standardizing it. We worked with VITA to get it into VITA 48.2. And it's there now, so it can be used and people can design to it. In fact, we've done some design work with it as well. I don't know if there's any product that's hit the streets yet using it, but it is available. So, but the one shortcoming was that while it's smaller than 3UVPX, it's only about 1/3 smaller than VPX, and we wanted something that was more on the range of 60%, 65% smaller than 3UVPX to really address these small systems.
Okay, and I've got a long question here from an audience member who said they're relatively new to MOSA and SOSA, and they have I have a couple of questions. So I'm going to start off with maybe go question by question, Mark, because I think it was focused on your presentation. They're saying that this seems to really push for a centralized architecture. Such large connectors and enclosures, even for VITA-90, really force smaller aircraft to have a single avionics user rather than a nice distributed approach, which can make it so individual components, say motors or individual, are swappable with a standard interface, thus stifling innovation and honestly going against the idea of open interfaces at the subsystem level. Are there any thoughts to using an already developed standard, say CAN Ethernet, without connector requirements for smaller vehicles? He has other questions, but I'll get to that one first. Yeah.
So, I mean, that's one of the nice things about VNX Plus is that it actually does permit for cabled solutions. So, say you were constrained and you couldn't put everything into a chassis, all nice and neat in a row and what have you. You had to put a piece here and a piece over there on the other side of the vehicle. You could actually achieve that, through cabling, whether it's copper cabling or flex cabling or something like that. So that was another reason why we kind of went down the VNX route, if you will, for that. That is a problem that we're constantly wrestling with is how do we deal with these perhaps you might call them unconventional approaches to system integration that sometimes are forced on integrators of these small systems, and we're hoping that we get pieces together to actually do that.
And why has the type of enclosure been included with the certification? Why is a backplane included, which only works well for CubeSats from small CubeSat form factors anyway?
SOSA itself is more focused on interfaces, and backplanes are kind of a convenient way to do interfaces for modules like this. But like I said, you could basically make a more or less virtual backplane by using flex cables and the cable version of the C-ray connectors to make your system a little bit more distributed. I hope that addresses the questioner's the viewer's question.
Okay, I got another question here for Roger. SOSA is based on OpenVPX, but isn't that too big for most unmanned vehicles?
Well,
Mark was talking about the solution for
Mark
right?
really did cover that. There are quite a few large vehicles, like these robots. Some of them are small, but some of them are big enough. And the point is that if you need the compute power, if you need the artificial intelligence engines, if you need this autonomous operation, you're going to need to house it in something, that's reasonable. And so the 3U VPX chassis, while it's larger than the VNX or the VITA-90, it does fit into quite a large range of existing and future unmanned vehicles. I mean, look how big Global Hawk is, for example. It's quite a large craft, and even some of the unmanned underwater tubes are quite large. So there's a place for 3U VPX in SOSA, and as the industry moves towards the solutions like Mark was talking about, the same principles will flow down to them. But there'll always be a reasonable case for the 3U VPX, especially, probably more so than the 6U VPX, is what we're seeing. We're seeing a lot more customers in 3U than 6U.
Yeah, I agree with that.
A question for Mark, more along this line. Are you trying to position VNX Plus as a VPX replacement?
Oh, absolutely not. So one would better to say that VNX Plus is a complement to VPX, and that what we're trying to do is we're actually trying to leverage all of the strengths of VPX, the modularity, the interconnectivity, especially thin, and keeping it in alignment with the SOSA principles. It's very important. Everything that we add to the standard within SOSA, at least we're testing against those principles to make sure that we're not breaking something, number one, and number two, that we're actually kind of enhancing VNX to support those principles. So I would call it more complement.
I would also say that a lot of the new solutions that are favored, like the artificial intelligence engines and so forth, they do require power, and it's really tough to deal with power in a very, very small box, which is exactly what Mark said. 3U VPX has a lot of conduction cooling and liquid cooling options that are well, developed and ready to go to handle watts, 100 watts, 150 watts on a card. So that may drive, VPX for a long, long time into the future because of its ability to handle higher power compute engines that will be needed.
Okay. Question for Roger, and I guess you can comment on this as well, Mark. Are you already seeing government opportunities specifying SOSA? I guess they're specifying
Yeah.
SOSA aligned, right?
They're specifying open system architectures, and there are several of them. And I think the whole thing is we're going to start seeing it shift from more general open system architecture to SOSA as time goes on. It's already starting. We're seeing bids. We started seeing bids coming out over a year ago that were inspired by the initiative. It's just going to get stronger and stronger. And the last part about that is that people who submit bids to the government for consideration in a competitive situation, those bids that contain the highest levels of SOSA will probably be favored very strongly over those that don't. And so it's going to become a competitive advantage for systems integrators to employ SOSA so they have a higher chance of winning.
I'd also add, though, that even if a proposal doesn't specifically call out SOSA or MOSA principles in general, it makes sense to actually consider leveraging the infrastructure that's being developed to support SOSA. I think we're really starting to get good evidence that systems are integrating faster and easier using these products than was previously experienced. And so, I think any integrator should pause and say, maybe we should be thinking about doing this well with SOSA components if we can do it. It just seems to come together so much faster and easier.
Roger, earlier on, you mentioned how the certification process, and they're trying to figure out that business model. I was at a press conference in the fall where they said maybe a year from the announcement of the technical standard 1.0, you might see conformant testing be ready to be set up. Is that date still doable, or is it being pushed out a little bit?
I still think it's a little optimistic. I had a really good conversation at the Tri-Service interoperability event that took place in February, I guess, and they still feel that it's moving slower than expected, and 6 months I think would be optimistic. I'll just say it that way. Somebody's got to get a business case that works for them, and then it'll take off.
Yeah, but in addition, it's a tough problem. I mean, I work on the conformance subcommittee, and I worked on one of the conformance matrices for just one slot profile type, specifically the IO intensive slot profile, and it had something on the order of about 350 conformance points that needed to be documented.
Wow.
They needed the process for testing the conformance point needed to be defined. The pass-fail criteria needed to be defined. It's not easy.
Yeah. Would question mark, would a switch card be easier in your opinion to start with?
No, it'd be just about the same order of
About the
magnitude.
same. Okay.
Yeah.
Interesting.
Yeah.
Okay.
So, Mark, to follow up a little bit, when I go to the Exponential show or other shows for unmanned systems, and I see the different products being offered from a small form factor side, VPX is I'm sorry, but Vita products aren't everything. What about SOSA considering maybe ComExpress or other small form factors as you're being on the small form factor committee? Are they looking at any other small form factors for adoption further on? Because they are pretty popular.
They are popular. And in fact, the first thing we did in small form factor subcommittee is to do a trade study. And we looked at virtually every kind of small form factor, even like little Beagle boards that you buy from SparkFun or something like that, to see, whether they could be made to address SOSA principles. And the biggest differentiator was the lack of scalability. You can't really scale ComExpress. You can't really scale things like a Beagle board or what have you. PC-104 you can scale, yeah, but its stacking nature kind of limited what it could do and how far it could scale. And so the closest one was VNX. And like I said, even VNX had some serious things that needed to be addressed before it could be useful for SOSA.
Okay. Roger, one of the things you and I have talked about over the years when it came to unmanned systems payloads was the trend and really the requirement to get as much signal processing closer to the sensor. How do MOSA or SOSA or any other open architectures help make that happen a little more quickly and a little more effectively?
Well, I think in the example system that I showed, where you have a subsystem up next to or behind the antenna feeding optical gigabit Ethernet payload data down to the 3U CPU chassis. That's an example of using SOSA for the DSP and the GPU and the artificial intelligence processing boards, but connecting to it over SOSA compliant interfaces, which is basically multi-gigabit signals over optical in many cases. So we're taking advantage of it, but we're not trying to extend the SOSA domain, if you want, up to be just behind the antenna where it really doesn't make that much sense. The interfaces are the really important thing. And the protocols, the VDA49 protocols, you want those to be compliant with SOSA traffic, even though the enclosures may not be SOSA controlled.
Excellent point. And I'm thinking about the drive toward commonality, which is a lot of the things behind MOSA and the Modular Open Systems Approach. Obviously, and ostensibly to lower cost. Years down the road, we can't afford F-35 programs anymore, and all that code. And it's not just software, not just hardware; it's all of it together. And you look at the different programs throughout, and one of the ones that came on early on was the Common Ground Control Station push within the DoD to get so they didn't have to use a different ground control station for every unmanned platform. And it was kind of at a more macro level. Now we're getting down into the component level with these different open architecture initiatives. Why do you think? I mean, there's been initiatives over the decades, we've all seen them, that have kind of gotten high and then failed pretty quickly. Why does this one, SOSA or MOSA overall, having so much enthusiasm and so much momentum? Both of you to answer, and then we'll kind of close out after that. Roger, you want to go first?
Yeah, I basically think that for the longest time, the military has been burdened with the fact that every time a new system comes out, we start over from scratch, and the expense and the time to get that new technology deployed in the field. So I think it's a huge benefit to our government, to the customer, to make SOSA really work for them, because it can, and it is working for them. So it's time for deployment. It's shortening. The risk is less. The cost is less. The ability to insert new technology is much easier. You don't have to start over. You can replace a SOSA compliant module with another one much more easily under this plan. So it makes sense. And if it makes sense, people are going to do it.
Mark?
Yeah, so I think what makes this different is that in the past, you look at standards going back to ADA, and even though it ended up being successful in the end, SCA, the Software Communications Architecture, they were largely government standards that were then presented to industry and say, here, make stuff to this. And I'm not well, and so SOSA did something different. What SOSA did is the government said, look, let's form a consortium with industry and with university academia, and the government will participate, but the government's not going to mandate. Let industry figure out how to do this. We'll pose the problems, industry come up with a solution, and when everybody agrees to that, then the industry's already got investment. They've already participated, if you will. And so I think that change of approach is what made SOSA successful.
And also, I think another reason I would just throw onto that is what Ilya Lipkin often says is that they didn't reinvent the wheel. They actually used existing standards to adopt into it.
Exactly true. And they use proven standards. So instead of inventing new ones, what SOSA always does is try to encourage the standards organizations to create new standards, and then they will adopt those standards.
Yep. And thank you, gentlemen. That brings us right to our time limit for session 3. Sorry we can't get to all of your questions today. Someone may get back to you after the event with more information. I want to thank Roger and Mark for speaking today, and Mercury Systems and Elma Electronic for sponsoring this session, and Wind River for sponsoring the overall event. This and all Open Systems Media virtual events are copyrighted and may not be recorded or used in any way without the express written consent of Open Systems Media. This session and overall event will be archived online today and be available for 1 year. There'll also be an MP3 version of the event available. Thank you for attending the Unmanned Systems Virtual Conference today. We look forward to seeing you on future military embedded systems virtual events.